Now we shall try to discuss the condition for equilibrium of rigid body. Now see, whenever the rigid body is said to be in a mechanical equilibrium, if both linear momentum and the angular momentum are not changing with time. So linear momentum should also remain constant and the angular momentum should also remain constant with time. Okay. The body has neither linear acceleration nor angular acceleration. See, first of all, we talk about translational equilibrium, that is linear equilibrium, or we can say we talk about linear momentum first. Say, for example, there are n forces which are acting, and total force is the resultant of all these forces. So we have to carry out vector sum, and if this force is 0, then no external force is acting on the body, then we can say that linear momentum of the body will remain constant. Okay, so this gives the condition for translational equilibrium. Now when we talk about the rotational equilibrium, then all the torques which are acting, we must have its resultant to be 0. So no net torque acts on the rigid body. So there will be no, we can say, the angular momentum of the body remains constant, or we can say the total torque acting on the body is 0. So total angular momentum does not change, it remains constant. So the rotational equilibrium is obtained. It means that if we talk about the forces, then x component of force, y component of force and z component of force must be equal to 0. All the three components are 0, it means resultant force is 0. So we can have the linear momentum is conserved, and if you have the x component and y component and z component of the torques to be 0, then there will be no torque in x, y or z direction, and we can say that it is in the rotational equilibrium. So there are 6 independent in scalar form for condition to be satisfied with the mechanical equilibrium. 6 means 3 components of force and 3 components of torque must be 0. So the sum of the components of the forces along any two perpendicular axes in the plane must be 0. Then the sum of the component of the torque along any axis perpendicular to the plane of the force must be equal to 0. Okay, so then there will be a conservation of linear momentum and conservation of angular momentum, and the body is said to be in mechanical equilibrium. Now we talk about the partial equilibrium. Okay, now you consider this body which is a rod, okay, whose length is 2a. There is a midpoint here which is denoted by C, that is center of this rod. So length, the one side is A, length on the other side of this center is A, so total it becomes 2A. Okay, now we consider that there are forces which are acting in the downward direction. So one force is in this direction, the other is also in the downward direction. So you can understand it properly that the sigma f will not be 0. Sigma f will not be 0 because the forces which are in same direction will be added up. Okay, so the moment of the force at A and B will both be equal in magnitude and opposite in direction. So there will be a resultant force to be 0. Try to understand, this resultant force is 0, but if you want to find the torque, that is resultant torque, then here this torque will be perpendicular distance from the reference point multiplied by force, both are at 90 degree. So r cross f here, r is a, f sin 90 is 1, so one torque is af, which will be in this direction. It will try to rotate the object in this direction, and this will try to rotate in the opposite direction. Okay, so here sigma f is 0, but so we can say that sigma f is not 0, because both the forces are in same direction, so we can say that there will not be a translational equilibrium. Okay. Now consider a rigid body of negligible mass and length 2a. Its two ends A and B, which A and B of which two equal and opposite forces are applied. Now we have a different case. Two equal and opposite forces are applied. Okay, one force is in this direction, the other force is in this direction. Okay, equal and opposite forces are there. Now we find the direction of the torque. Then with the both the torques on the rod in the same direction. See, try to understand. The one torque is in this direction, the other torque will be in this direction. Okay, if one person is taking or rather applying the force in this direction, the other is in this direction, what will happen? This will try to rotate in anti-clockwise direction. If table is there, say for example you have a table, one person is pushing in this direction, that is his force is in this direction, the other one is pushing in this direction, what will happen? This table will rotate. Okay, this will rotate in this particular direction. Same phenomena occurs when two forces are equal in magnitude and opposite in direction, they are at different point on the rod. Then what will happen? This object or rather rod will try to rotate. Hence both the torques on the rod in the same direction cause the anti-clockwise rotation of the rod. So the rod will try to rotate in this particular direction, that is anti-clockwise direction. Okay. So the total force on the body is 0. So the body is in translational equilibrium. It will not move in a linear motion, but it will have a rotational motion, so it is not in a rotational equilibrium. And if rod is fixed at point C, then it will undergo pure rotational motion. Okay. So this happens when the point, or rather we can say the forces are applied at two different points. And here there will be a translational motion. The object will move in this particular direction as the forces are in same direction. So the rod totally will move in this direction, and this will try to rotate in this direction, and this will try to rotate in the opposite direction. The torques are equal in magnitude, as I calculated AF sin 90. So one is AF, but it will try to rotate in this particular direction, that is this direction means it is in a anti-clockwise direction. This will try to rotate in this particular direction, so it is a clockwise direction. So both the torques are equal in magnitude and opposite in direction. So we can say total torque acting on this will be 0, and this will remain in the rotational equilibrium, and it will perform the linear motion, that is it is not in the translational equilibrium. Okay, the thing that is explained that I have left, but purposefully I did it, because if you understand this part properly, second part, then you can easily understand the first concept. Okay. Now we talk about the couple of the force. With the illustration we see a pair of equal and opposite forces with different lines of action is known as the couple of torque. Yeah. Okay, couple of the torque, we can say a couple or a torque. A couple produces rotation without translational motion. Try to understand the handle of the scooter. If you have the handle of the scooter, and if you want to move in say right hand direction, then what will happen? You will pull this in this direction and push in this direction. The left hand of your body will push this side of the handle, and the right hand will pull it. Okay, so what will happen? This will rotate in this direction, or we can say in this particular direction this will rotate, and you can take the turn towards right. So equal and opposite forces. See, these are the two forces. By just we are having this in our unconscious mind. Okay, we are applying the equal and opposite forces. Try to understand when the handle is there, that of the scooter, and if you want to go this side, then you are pulling this handle towards you and pushing this side of the handle away from your body. Okay, so it will rotate like this and it will give you the right turn. Okay, try to understand these are the two forces which are giving the torque, which is couple, which is known as couple of the torque or couple which is produced here. Okay, one example is given here. If you are rotating the, if you want to open the cover of any bottle, then you are by this finger you are pushing it this side, and by the thumb you are pushing it the other side. Okay, so what you are doing, the equal and opposite forces you are applying, force in this direction and this is the force in the other direction, that will rotate the what you call it, cover, and it will get open. Okay, similar thing happens whenever you have a magnetic needle. One force is acted upon by on north pole on one side, on south pole it is acting on the other direction. Okay, so what will happen, equal and opposite forces will rotate, and after some time it will become steady in the north south direction. Okay, when it is steady, what is happening, it is in the north south direction, it is steady. Both forces have same line of action of force, but except this direction the line of action of force is not same, and due to magnetic field of the earth couple acting on the needle, so it undergoes rotational motion without translational motion. So whenever it is in equilibrium, equal and opposite what you call it torque acts. Okay, and it is said to be in equilibrium because their same line of action of force will be there. Okay, so the needle will remain in equilibrium. Except equilibrium position it will rotate, and you will have the couple of the torque which is acting on the magnetic needle. Now see, you must have studied the different types of lever in your lower standard. First type of lever, second type of lever. Simple example I am taking. Say for say you have this very big rod. Okay, you have a big rod like this. Okay, or we can think of like this, that if you have a load, this is a stone, heavy stone is there, and if you want to move this stone from its place, and what do? Generally we take a very big rod, we put some support here which is named as fulcrum here. Now what do? You just apply the force in this direction. So this will be toppled down, it will go the other side. Then again you fix this whole system, and slowly you can move this stone to the different place, or a heavy load to the different place. Now what you are doing here, you are applying the effort, and here this is the load which you want to carry, or you want to just push this from one place to the other, and this is known as the fulcrum. It is denoted sometimes by F in different books, but in our textbook a very simple concept is explained here: construction and working of ideal lever, and also explain the principle of moment of force. Now the same things are explained here. Here there is a center point, or we can say some support is there. It is pivoted. A rod of negligible mass is pivoted at the point which is shown here. The point is called the fulcrum. This lever is a system in mechanical equilibrium. Okay, now see different forces which are acting, which are shown here. See, two forces are acting. Okay, one force is in this direction F1, that is, say some load is kept here. Okay, you want to carry and load is having its mg force in downward direction, and you are applying the force F2 from outside. So there are two forces F1 and F2. Okay, now the distance of these two forces from this equilibrium point or a fulcrum, they are d1 and d2. One distance is d2, the other distance is d1. Now see, whenever this kind of system is there, then we have this is the system of the what do you call it, lever. Now see, these two forces are in downward direction, not in equilibrium, they are in downward direction. One is F1, the other one is F1. Reactive force is in the upward direction, and upper direction force, if I take positive, then R minus F1 minus F2 will be equal to 0. Why? Because this rod is neither going to perform the motion in upper direction nor in the downward direction, so it is in translational equilibrium, or it will not move or it will not perform the linear motion. So that is explained here. R is equal to F1 plus F2 because it is R minus F1 minus F2 is equal to 0. The lever force F1 is some weight to be lifted, which I tried to explain. What is F1? F1 is nothing but a kind of load which is to be lifted. So here there is some stone or something which you want to lift, and its downward force F1 is because of its weight, that is mg. Okay, and this force is applied by you. Okay, so what will happen now when you are pushing this in downward direction, this will be slightly toppled and it will go to this side. Okay, you want to lift it. Now see, the distances are d1 and d2, that you can see. Now see, torque, if you want to find, then this torque is R cross F, that is D cross F. So one torque will be d1 F1, the other torque will be d2 F2. Now see, the angle between d1 and d2 is 90. Okay, so one torque is d1 cross F1, the other torque is d2 cross F2. So the d1 F1 sin 90, it becomes, see, d1 F1. So d1 is the vector this side and the other one is in this direction, 90 degree angle. So d1 F1 sin 90, so it will be d1 F1, the other one will be d2 F2. Okay. Now see, the one torque is going to produce the rotational motion in this direction, that is what you call it, anti-clockwise, and this will produce clockwise direction. So two torques are in opposite direction, so resultant torque will be tau 1 minus tau 2, and that can be written as d1 F1 minus d2 F2, no vector now, and it will be equal to 0 if it is in equilibrium. So we can say that d1 F1 is equal to d2 F2. Okay, so d1 F1 is equal to d2 F2. So d1 is nothing but load arm distance multiplied by F1 is load, d2 is effort arm distance, and F2 is the load or rather effort which is applied by us from external means of force. The above equation expresses the principle of moments for a lever. Here this ratio F1 upon F2 is called mechanical advantage, which is nothing but d2 by d1. Okay, if d2 is large, say d2 is large only. Okay, so if d2 is large, then if you are applying the less force, then it becomes a force multiplier. Okay, so if F1 which is acting, or rather F1 which is force acting on the load, or rather load is to be lifted, will be d2 upon d1 into F2. So if you have force say F2 is very less, then also this resultant force which is acting on it, the load rather, F1 will be D2 F2 upon D1. So D2 is larger than D1, so that force is multiplied. If the effort arm D2 is larger than the load arm, the mechanical advantage is greater than 1, means that small effort can be used to lift a large load. The principle of moments holds even when the parallel forces F1 and F2 are not perpendicular but act at a certain angle. Every time this is not there, if we are applying the force in this particular direction, say slightly slanted, then also this law holds, okay, and this principle works. Okay, thank you very much.